70s, yeah? Why don't you just tell us a little bit how you...
Oh, you want me to tell you about...
it's a great story, yeah.
Well, actually, it's an amusing story, but I don't mind telling you because I don't have that much to tell you about this, except the fact that I know you're interested in this, and I think it's important. And, what was happening is I was a graduate student at the Krant Institute, and I needed some extra money on top of my fellowships. I would look for a summer job at NASA's Goddard Institute for Space Studies, which at the time was led by an astrophysicist called Jastrow. And I'll skip a lot of the details, but in any case, at the time, Joe Charney, who you might know was, he was maybe less well known outside meteorology than Ed Lorenz, but he was a heck of a lot better known within meteorology than Ed Lorenz. He had become interested in using satellite data for improving numerical weather prediction, and so it became apparent that, again, a great Scandinavian, Willem Jöknes, a father, had realized at the beginning already of the 20th century that numerical weather prediction is an initial value, should be an initial value problem for a set of partial differential equations governing the flow of the atmosphere, except that when people started doing this, John von Neumann and company in Princeton, they realized that they didn't have initial data, so you needed to do something different from the standard initial value problem, and the advent of meteorological satellites made it very obvious that what you needed to do is to somehow combine data with models in continuous in time. And so actually the story again has to do with Joe Charney because it was visiting him up in the Cambridge area, his home was in Brookline, that I met a guy who, Ed Sachek, some of you might know him, who said, oh yeah, my brother, is working in aerospace or something, and they have this thing called a Kalman filter. Oh, interesting. And
that was
all downhill. No, Kalman developed this when he was an engineer with, I think what was called at the time the Marietta Company in Baltimore, Maryland, to guide spacecraft, missiles. And so up to that time, really, people were doing very low-dimensional problems. Okay, if you look at the standard book that engineers were using, the ghil+brandenburg book, all the examples worked out at 3, 4, maybe 6 equations. So the idea that you could do this for partial differential equations, although there were some formal papers that said, oh, just do the same thing. It's when engineers do mathematics, they just say, oh, instead of writing a differential operator, write a partial differential operator. But of course, there are all sorts of problems. You can't even define white noise in space and time properly. You need some special function spaces and so on. Anyhow, this is, that was a heroic period that I talked about on Friday morning, and I've been doing lots of other things. And actually what I was presenting at that meeting had more to do with time series analysis, the signal spectrum analysis and various things like that. But what I wanted to say today, when I finally got around to look at what this meeting is that I was invited to, actually had to pay for my plane tickets, I realized that there are 2 paragraphs, and the second one was about the sun. And then I also saw that you're obviously doing some astrophysical turbulence, which I know about from some other colleagues that I have at UCLA, and I think that, well, this might be of interest. So really, this is just to say that I'm going to show you some stuff that basically just says it's important to do the sun. I don't know how to do it, but we can talk a little bit about that. So basically, these are my 2 affiliations, and basically pretty much all the papers and a lot of presentations on this website at UCLA and there's also some stuff on the website that we call Normal. When I moved from LA to Paris, I was told it's not good to move your website because people will lose track of you or something like that. So it's still one on which all the papers are, including, but the one that I'm talking about is the Geophysical Research Letters, which I hope you will be having. You have access to here. If not, then just you have a PDF. So basically, okay. This actually, I had to translate it, this slide into English because it was presented, there was a meeting at the French Academy of Sciences some years ago about global warming. You know, there are some miscreants in the French Academy who don't believe in global warming, whatever. And so there was a meeting organized, and I presented something, and there's still one sentence which is in French because it's an allusion to a common French saying. So, okay, so some climate relations. Well, it ain't exactly new. See 1,000 papers. So this is actually, so I moved from the Grant Institute, where after doing my PhD, I was on the faculty for a while, to UCLA in '85, and chair of the Department of Atmospheric Sciences at the time was George Sisko, who is maybe known to some of you because of his important work in the Earth's magnetosphere and so on. And he brought to my attention that some years ago he had written, so there was a climatology supplement to Nature at that time, about solar terrestrial influences on weather and climate. And at that time, so in 1978, it says, during the past century, over 1,000 articles have been published claiming or refuting a correlation between some aspect of solar activity and some feature of terrestrial weather or climate. Okay? Nevertheless, a sense of progress that should attend such an outpouring of results, in quotation marks, has been absent for most of this period. The problem all along has been to separate the suspected sun weather signal from the characteristic noisy background of both systems. I would say that the situation has not changed. Okay? I mean, again, he goes on to say that there are some correlations which are maybe more significant than others. So my second sentence here is there's a, you know, in French you say comparaison n'est pas raison. The fact that two things look similar doesn't mean that they really are similar, so I say corrélation n'est pas raison. You know, there are well-known correlations between the length of skirts on the solar cycle and between
that could be explained.
Yeah, the number of Republican and Democratic senators. There's also about which one of the two football leagues carries away the Rose Bowl. That's also one that's very important for real Americans, you know, red-blooded Americans who follow football. Okay? So, you know, I really, you have to realize that during the years many years when I was mostly doing my professional work in the United States, I was on various committees of the so-called National Research Council, climate research, and various other things. And typically what you do on such committees, I don't know about Sweden, but certainly in France and the United States, which I know better, is generally you speak for how important what you do is for the good of humanity. Okay? So it was very rare for people to say that you know, solar physics should be funded. Okay? So I had this sentence, I didn't put it in today. This is translated from French, and it is actually part of the conclusions of this paper that I now want to come to. Okay, so this was a paper in Geophysical Research Letters. Okay, models of solar irradiance variability and the incremental temperature record. This is a former student of mine, Steve Marcus, who's still at JPL. And Kaya Ide was at the time a postdoc of mine at UCLA. She's now at the University of Maryland. So, you know, basically, we use two proxies of solar irradiance. So, I don't know. I mean, obviously, there's a fairly large group of people here, so I assume that this is something that is indeed a preoccupation of. You probably do know that there are no measurements of total luminosity, you know, total solar irradiance, TSI, that go back very far into the past. I mean, there were some satellites, and because of the way that space agencies work, there wasn't a lot of continuity between the coverage of those satellites, so there are all sorts of difficulties. I mean, you know, we've now observed instrumentally 2.5 or maybe 3 solar cycles, but the so-called decade-to-get-decade or interdecadal variability between one, you know, the mean activity over a cycle and the other is not very well known. So, of course, there are sunspots and there are plages and there are all sorts of things. As a matter of fact, I shouldn't mention in front of such a large audience, but I can tell you actually separately, you know, the coffee I keep or whatever. I was solicited by 2 fairly well-known people in this area from JPL to join a project with them. Okay? And one of those 2 people is famous for one reason, and the other one is famous for another reason. And the other one is because he used to do some very important work in turbulence and so on in the pharmaceutical unit. Okay? And so I was hoping when I joined them that I would have an opportunity to work on solar physics. Okay? I should also mention that for those of you who are not familiar, that I have a book that was written with Steve Childress, who some of you I'm sure know from his work on the geodynamo rather than the heliodynamo. So I knew a little bit about the dynamo and the kind of simple models that Steve had done for the geodynamo, and was hoping for something like that with these people. But instead what I got is that every time I went to JPL, so I used to go about once a month to JPL, they had something they call a distinguished visiting scientist, you know. This other person would show up and come, well, they would show up both, and this other person would have a new proxy which had 2 very important features. One is that it was totally independent of all the previous ones, and the other one was that it was perfectly well correlated with it and demonstrated that indeed the sun, you know, drives climate. Okay? So, anyhow. So, okay, this is just for a little bit of background. And now, what did we do? We had a very simple model, you know, sub-toy model, in which this W is the total irradiance, and this is some sort of relaxation time, and this is, the irradiance anomaly is driven, okay, by something. And I'm sorry, the K1 and K2 are reversed, but we had what's called a cycle length model and the cycle decay rate model. Now, why cycle length? Well, something that you know that solar cycles are not born equal. Some are a little bit longer, some are a little bit shorter, and it's well known for anybody who's done sort of nonlinear oscillations that typically amplitude and period are correlated. So in some sense, the length of the cycle is a proxy for its amplitude. Okay? And the other one, I was told, and I don't know why, that the cycle decay rate is supposed to be a better proxy, that it has something to do with the turbulence in the convection zone. But you'll tell me whether that's true. So the model in one case is that you just look at the difference, that the length of the cycle, you know, the time of one minimum and the time of the next minimum. And here you're just looking at the difference in time between the maximum and the minimum. Okay? And if you do this, here is what you get. So you have essentially 3 curves. One is the anthropogenic forcing, so in other words, basically greenhouse gases, but from which you have to subtract the opposite effect of aerosols. Okay? And then the blue is the cycle length, and the red is the decay rate. And you see that one of them, you know, this one goes up during this recent time, so it's sort of It does the same thing as the anthropogenic forcing, and the other one does not. Okay? So the effect of this is that if you now look, so the other thing that we had in this paper was we actually had an energy balance model that was coupled with something that's called a very, very naive model of the ocean, a so-called upwelling diffusion model, and EBM stands for energy balance model. Okay? And so here we are looking at the cycle decay, okay? And then on the next one we're going to look at the cycle length. So if I look at the globe now, the blue is the global mean near surface air temperature. Okay? So it goes up and down, but basically does something like this. So, you know, this is instrumental temperatures. They were basically flat during the second half of the 19th century. They went up during the first half of the 20th century. They came down around here. As a matter of fact, many of you might not realize, you know, my PhD thesis, when I also became interested in climate, was somewhere around here. And the first interest in anthropogenic effects on climate was voiced at a conference here in Stockholm in 1972, which gave rise to it was called, to a book called The Study of Man's Impact on Climate, or SMIC. And at the time, really the concern was that we're going to fall into an ice age. Okay? There was actually, I don't have that here, but because I only have half an hour to prepare this talk. There is a letter that the Conference of Paleoclimatologists in the early 1970s wrote to the then president in the White House, a man named Richard Nixon, saying, Mr. President, you know, we trust that you're going to do something about this because we're in great danger of agriculture collapsing and so on, because of falling into an ice age. And, you know, of course, what you have to do is to fund climate research better. So, this is tongue in cheek, understand. But it's amazing because, you know, some of it talks about more extreme events and stuff like that, exactly what. So, it was going down, and then it's been going up since. Okay? So now, this says solar forcing only. Well, clearly, that won't work. But now, if you do add the anthropogenic effects, in other words, greenhouse gases and sulfate aerosols, you get the whole effect. Okay? With the error bars. On the other hand, if you just do the cycle length, then you can still claim that it's all the same. Okay? Clearly, you'll fit it even better if you include the anthropogenic effects, but you are not that much off. So the point of this really is that we should know about the sun. So that's, you know, that's what I was saying here. Okay? It requires serious modeling rather than those very naive things with correlations and so on. And then, oops, something else that we did, and I don't want to go into the details but we looked at, you know, the solar forcing is also used as a proxy of climate sensitivity, so there are some graphs here. So these are just repetitions of the graphs that I showed you in greater detail. But, you know, papers in GRI, like in PRN, can be only 4 pages long. So, you know, it shows that what's plotted here in color is climate sensitivity in terms of degrees Celsius for CO2 doubling as derived from the results of those two models. Okay? So this is just intensity in watts per meter squared, and this is so this is solar forcing, only solar plus anthropogenic, and likewise this is for the CL, that's for the CD model. And this basically again tells you that the features of climate sensitivity that you're going to get out of this are going to be very different depending on which proxy you use. Okay? So basically that's all I wanted to show by the way of an introduction to this open discussion that Axel suggested. And again, you know, of course, by now there's a whole, you know, in climate modeling we use very actively the concept of a hierarchy of climate models, from little silly, you know, toy models like that, all the way to global climate models or general circulation models, which occupy large computers. And in solar physics also, I mean, there is a high-end type of model, like the ones which are being used at the High Altitude Observatory of NCAR and so on, but there are also some little toy models like these of, you know, Paul Roberts and Steve Childress and various other people for the geodynamo. So, you know, my attitude in climate modeling has been that you have to start with the simple ones where you can still understand what they do, and build your way up to the really big ones, which then you can compare in detail with some observations that you have. So, I don't know, now I want to hear what you're doing here, and to which extent any of this is relevant.
Yes, maybe let me start first of all by asking, is f of t like maybe Michael, is f of t the driving from the solar dynamo essentially?
Yeah.
And what is then the
well, that's just some decay time. I mean,
so that would be on that could be the Kelvin-Helmholtz time scale, which can be fairly long.
Yeah.
I mean, it can be a million years, in principle.
Okay, well, then obviously we didn't use that.
But you want something that is shorter than...
We want to look, I mean, I think that what you would all like to see is some modeling that is valid on interdecadal timescales. Okay, from one cycle, you know, cycle to cycle variability. So that's a sort of thing that you would want in order to replace the red curve and the blue curve. Okay.
So the thing is, of course, that total irradiance is not necessarily the relevant quantity, because if the greenhouse gas will have different absorption bands and this and that. So as I see here, we have two problems. One is that we have a fairly short record in the sense of the sort of variability, decadal variability here. So we basically want to correlate either of these three curves with the global temperature curve, which is probably not information enough to really constrain if one of the other facts is the most important one.
Well, recently, I mean, I understand that there has been some work that indeed has tried to separate into spectral bands. But let's just say that in terms of temperatures, what people do, the way that they use proxy records to extend the temperature record, things like that, into the past, is to say, okay, I'm trying to correlate over the time interval over which I have instrumental data, okay, some sort of proxy with the actual instrumental data, and then extend the record into the past by using the proxy. So there are all these things, you know, some spot numbers and whatnot, but you would have to really correlate them with something that makes sense over the last 150 years, you know, to the extent that we have reasonably good temperature data since the middle of the 19th century. We have about 150 years, so that's about 12, 13 solar cycles. So it would be good to have to systematically look at results of irradiance, if you don't like the total one, but you know, the appropriate higher detail in spectral space for the last 150 years, and try to do this sort of exercise for such a model.
I mean, so there's questions on the solar side and on the climate side, of course, but on on the solar side, we have already a question whether, for example, the measuring of sunspots has much to do with the forcing. That's one question already. We clearly know that the magnetic field is varying, and we also know that the magnetic field has an effect on the beryllium modulation, for example, in the ice cores, which is not terribly well correlated. I mean, in particular, during the morning minimum, we know that we have the solar cycle, which we don't see at all in sunspots. So clearly, there's a great mismatch between magnetic field and sunspots.
Yeah,
and radiance probably also, yeah. But that we don't really know that much in the past.
So in terms of these relations between cycle length and decay rate and so forth, the about best performance they do in terms of predicting the next cycle is to guess the mean. So they perform. Their performance is not very good. There is some kind of second order where you combine different proxies, and then you can maybe get a factor of 2 better. But most of these proxies are basically worthless because they perform the same as guessing the previous mean, which is not useful for anything. And then, of course, tries to introduce and incorporate physical models and see how they can improve the performance. There is another set, and that is curve fitting. That when we are inside a cycle, it's kind of possible to make a curve fit and fit the current cycle. And then we also have the third set of things, and that is looking at basically long-term variation. And there's a lot of talk about the 200-year cycle and the 92-year cycle and the 500-year cycle. And that is a picture that one could argue that it could be used to kind of see a long-term modulation, and those are kind of the different groups.
How well established are these long cycles from the sort of solar physics?
This is carbon 14. I mean, this is more.
But you know, I mean, that's a long discussion we've also had on how significant are periods. You know, what do you compare with? And then obviously the solar output is not like an Ortspan-Uhlenbeck, it's something else. So how would we know that these periods are significant?
I'm not so worried now about these very long periods, but I was going to suggest, something else that, again, somewhere between actual physical modeling and, generalized curve fitting, there is this business of using different kinds of models of a process based on data. And I guess, is John T. here? No, I guess he decided that he had something else to do because, it would have been interesting to have his input. What Peter was alluding to is another piece of history that somebody picked me as his opponent for his DSC. And actually, Peter is more of a turbulent guy than a cycle guy, so he actually, at the end of his presentation, showed, had a very key thing about, a camel, and whether that shows that you can extend the 2 humps of the camel, into the future or the past. So, there is a connection to the talk which I will give on Wednesday afternoon, I guess you're saying, which deals with empirical model reduction, or EMR, and these are nonlinear models that are data-based, you know, and do allow for, well, in principle, an arbitrary order of nonlinearity, but in practice, because of the trade-off between confidence and amount of information, typically quadratic, which, again, you know, look like this, that, let's say you have here some sort of a quadratic function, so this is just to indicate that these are vectors, okay, and then you might again have multiplicative noise, something like this, okay, with some sort of a Wiener process, and that doesn't need to be white, it can be reddish. And we've had considerable success in modeling. So these can be applied either to data, in other words, the data can be either observations or detailed simulations of bigger models, you know, models spread up the hierarchy. And we've done quite well with these in terms of so-called seasonal to interannual prediction of the El Nino Southern Oscillation, you know, things like the Southern Oscillation Index or the various sea surface temperature anomaly indices, Nino 3 or 3.4, something like that. So these are quite competitive with, there is something that is called the forecast. There used to be something that was called the ELNFB, the Experimental Long Lead Forecast Bulletin, which used to be published by essentially the National Weather Service, and now it's published by something called COLA, which is a not-profit research center for ocean, land, atmosphere. And more recently, there's something which is called the Forecast Plume of the International Research Institute for Science and Society, for Climate and Society, sorry. So you can look this actually up. And this one now has something like 14 dynamical models, which can be big coupled GCMs. And I forget exactly how many, maybe 7, maybe more, 9 sort of statistical models. And this one is clearly doing quite well.
Those are the ones going into the IPCC?
No, this is seasonal to interannual. This is S to I. Seasonal to, it's not interdecadal. No. We have an improvement on this, which is now under review in the PNAS, in the Proceedings of National Academy of Sciences, but I'm not talking about that. I'm just saying this one is quite competitive with the ones with this. If you look at the IRI plume, you know, they are planning now, the IRI is planning to have a second generation version of this forecast plume. So, you know, the forecast plume just tells you this is time in month from these forecasts are issued on a quarterly basis. So every 3 months, you know, there's a forecast, etc. And in principle, it's plotted out to something like 12 or 14 months. But most of these things are, so it's called a plume because you see all these different forecasts, and you can see. And actually, if you go on the website, you can click. You know, these are all listed here, and you can click on one of them, and it will show you what that particular forecast did over the time. Okay, so we're really doing quite well, and we will be in the next generation. I don't know exactly how many forecasts they will retain out of these, but what I'm trying to say is that it might be interesting to use something like this. That indeed you can do what's called hindcasting. You can try to test your model, not just how well it fits a curve, but how well it forecasts. And, you know, of course, this has to be done carefully. There's something that is known in the trade as no look ahead. In other words, you really have to make sure that when you do this hindcast, you're not using any data beyond the point from which you hindcast or retrospective forecast. Okay? So this, in some sense, is a more powerful test in just curve fitting. Okay? Yeah?
I think now that you're talking about that, I think our group is trying to do something similar to that, where we have a very simple model that is trying to catch up the relevant aspects of, for example, the solar cycle. And then from there try to build a consistent estimate for the parameter values and the forecast. So you generate an ensemble that is going to be the best one you can produce to have the best forecast somehow. And it will follow the model inside the window where you have observation.
Well, I mean, you're talking, this model of Ed Spiegel's is essentially the kind of thing that I had in mind when I associated myself with the person that he knows. Okay? And instead, that person published a paper on Earth is climate, which I will refrain from commenting on. Okay. Had something to do with stochastic resonance, which is a lovely phenomenon in all sorts of fields of physics, but is not one that I'm particularly convinced by in climate variability.
So if we look at sort of the physics of the problem, of course, I mean, I would rephrase the question of the sun influence on the climate. Try to turn off the sun. Of course, the sun governs climate. And when the sun governs climate, the variability, the ghil variability is also in there somewhere. But now, the reason that you have 1,000 papers and the situation is not clear is, of course, there's an enormous natural variability on top of that. And I would say that's really what is the problem. Is how would we understand? How do we improve on the natural understanding of the natural variability? And that's probably hard to get at with simple models with few degrees of freedom. Yeah. So somehow, to me, it's trivial that the sun, of course, whatever, if we knew how the sun did, the signal would be there somewhere. It might be way below the noise level, but there's no question it's there. The question that really needs to be answered is, how predictable is natural climate variability, right? If it's sort of an statistical thing. That's I see.
And serious scientists who are also good friends can still differ.
I mean, by natural variability, you should of course include things like volcanoes going off. Or
yeah.
do you not?
Well, I mean, that's semantics. That's semantics. Of course, I mean, volcanoes is outside. You could define your way out of what's inside and what's outside.
No. I mean, you distinguish between intrinsic variability and forced variability. Now, so the forced variability also falls into natural and anthropogenic. And of course, volcanoes are natural, but they're not part of the climate system on the time scales that we're talking about. I mean, the extent to which, large ice sheets could affect the solid Earth and therefore could affect volcanism on long time scales, that's not.
Of course, snowball Earth is important.
Yeah. No, but I mean, if you're doing curve fitting and looking at the variability of from one cycle to the next, then of course the influence of volcanoes can seriously offset any potential correlation between the two. And I think the last two minima, except the current one, have been coinciding with volcanoes. Certainly the Dalton minimum and I think the Monte minimum as well. Is that right?
Let me just say that since you mentioned some of these longer cycles, I mean, again, I once attended the University of Arizona has every year a conference related to the solar system. Typically they discuss one of the primaries, one of the major planets. That particular year it was the sun, and again there was somebody there. who said, you know, this was some years ago, so simple ideas about chaos were still popular. That person said, well, this is obviously period doubling. Okay? So this is the ghil+brandenburg cycle, which I think was cited here as being 92 years, but that person said 88. Well, you know, this sort of reminds me, there's a famous story about the statement that all odd numbers are prime. Okay? So, you know, yeah, say, how do you prove that? Well, here it says, you know, 2, 3, 5, 7 by induction. Then physicist says, you know, 3, 5, 7, 9 experimental error, 11, 13, it's true. And the engineer said 3, 5, 7, 9, 11, 13, it's true. Okay. So this was a little bit like that. There's no 44. Okay. And now, of course, the 11 is only the rectification of 22, and ghil+brandenburg was defined to be 88. So, you know, obviously it's period doubling. Okay. This you can actually look up. This volume was edited by Chuck Sonnet, and you can look up at the contribution that talks on period. Okay, so you know, clearly that's not what you want to. That's not the way you want to reason about these things.
So the 11-year cycle is, I guess, well understood from just the differential rotation in the sun. And so it's more like a decorrelation time, right? The 11-year, because I mean, you're basically swapping around the magnetic field lines until
but
they reconnect.
Yeah, it's not exactly clear why it's exactly 22 years, and not, for example, 3 years. That you could well argue about this on theoretical grounds. That is wrong about that period is okay, but it's not clear that it's.
So you need an order of magnitude.
And there's another issue. We know from observations of other stars that at least a third of all the stars that are late-type stars, which have outer convection zones, exhibit cycles, and they all exhibit a certain relationship between how fast they rotate and the cycle frequency. And that is a relation that nobody has seriously been able to address. Not even the best solar dynamo models are actually able to reproduce that. And so what I'm talking about is the following. Maybe I should leave it in space.
Yeah, you can erase anything that I've written.
So we have, we plot now the frequency of the cycle, the inverse period, and it divides this by the rotation frequency. And we plot this versus several different indicators we can choose, but one of them is the inverse Rossby number. So that's essentially the, again, rotation period, rotation frequency, times the turnover time. So that's non-dimensional, and this is also non-dimensional. And then you...
sorry, what time did you say?
That's the turnover time.
Turnover time.
Turnover time.
Large scale.
Yes.
Okay.
So that has to do with the turbulence. Another proxy that you can use, and it also gives a similar curve later on, is something which actually measures the magnetic field strength. And those two, by the way, are also very well correlated. Let me actually start with that one first. So if you, as you crank up the rotation period, but make it non-dimensional, what you do increase is a measure of the magnetic field strength in the chromosphere. There's magnetic field lines which are called chromospheric emission lines, and they are being excited by temperatures on the order of 10 to the 5 million Kelvin or something like this. These are temperatures which are higher than what could normally be in, I think now coronal lines. They are higher than what could be gravitationally bound in the sun, unless you have a magnetic field, a flux tube, which can confine such hot plasma, at least for certain periods of time. And so those lines you can measure, and that gives a proxy of magnetic intensity. And that's for some reason called RHK prime. These are calcium emission line measurements, and R as opposed to F, which is flux, is also 9 dimensions. And so, so first of all, this curve correlates with this one, approximately like this. These are power laws, with a slope of 1, by the way, and then it becomes saturated later on, and possibly even goes down. Now, so you can either take this one, or you can take RHK and this following plot, and this plot looks like this. It's an increasing curve with a slope of approximately 1/2. It's also logarithmic. There's a slope of 1/2. The sun is approximately here. Oh, forget now. Over here. And there's of course a bunch of stars which are scattered around this. These are all called the inactive stars. The sun is, in some sense, an inactive star. And then there's active stars, which also fall on lines. And it's a different line. These are active stars. All right, and for many of these stars, one has claimed to also see two periods, a longer one and a shorter one. So there are certain stars which have a period here and another period over here. And of course, this corresponds to 22 years, and guess what this corresponds to?
3 years.
No.
Oh, 88.
Yes, yes. So it has a smaller frequency and larger period, therefore. So this is the 88-year period. So it's not exactly, I mean, there's no reason why. First of all, it's not clear why this slope is, first of all, plot positive. On theoretical grounds, you would expect the slope to be negative. So it's major ill understanding of in dynamics theory. The best explanation that we have so far is still a very old explanation, and that indicates that the dynamo mechanism is actually becoming more and more intense as the magnetic field strength goes up. So unlike normally you have a situation that as the magnetic field goes up, you quench the mechanism that drives the magnetic field. And in fact, what we hear is quite the opposite. That's not all. There's actually another line which goes like this. And these are the superactive stars.
Which stars?
Superactive.
Well, superactive.
In what sense active?
In the sense that the magnetic field strength is very high. Because this is also a proxy of RHK here.
So, but how do you distinguish the I, the A, and the S cluster there?
Oh, there's simply 3 different populations. So you plot every star you can do. You take away those data which are not very reliable. If you take every data, that's some people do that. If you take every data, highly reliable ones and highly non-reliable ones, then you fill the whole plane. This white noise, of course. But if you only take the reliable data, you find that the points are on 3 different distinct populations. And these are typically stars which have rotational periods on the order of days only, very short. So yes, the negative slope of this one is theoretically understandable, but then the positive slopes are not, and it's also not clear why we actually have 2 different such populations. By the way, the separation between the two is well known in stellar physics. It's called the Vaughan-Preston gap. Vaughan-Preston gap.
And our sun is active?
Inactive.
Inactive.
Yes. If you want, I can show you the data. The plots. You want to see the plots? Yes. So the first one.
We're done.
What?
Yeah.
these are the stars from the literature, and this is the first paper on this. I think crash. And I can try it from Windows here. And that's when one wants to get something quick. Yes, here are the stars. So the middle one is, these are 7 stars, 5 stars, 6 stars. And this is more like the order of 20 stars, and they are all indicated by letters. And this is so the RHK parameter you see here. You also see, and here you see this ratio, cycle frequency to rotational frequency. You see the different stars indicated by numbers. The cursor is slightly obstructing here. You also see a time line. Often the RHK parameter is used as an age indicator for stars. And therefore it's actually clear that stars, as they get older, they evolve from this active line first, but then eventually must jump onto this inactive line. And so what causes such a jump is unclear. And then they evolve further along this line. And so the sun is...
isn't that, I mean, could it possibly be something like the transition between whatever, an omega alpha dynamo and an omega square dynamo? Or?
As I said, we don't even have a good interpretation. The best interpretation that we have is, in fact, it is an alpha omega dynamo. And if you do that, for alpha omega now in this case,
yeah.
it's not alpha squared, then this line would correspond to the value of alpha, and this would correspond to the magnetic field.
Okay.
And if you follow that interpretation, then you see that as the magnetic field strength goes up, the alpha goes up. But then it crashes and has a different line. So the only way that we can understand that an alpha effect in dynamo theory increases with magnetic field strength is if the alpha effect is caused by a magnetic instability, like buoyancy instability.
Let me just maybe, since there is a connection between this and the discussion we had about Valerius talk this morning, I mean, just show, you know, these used to be known to people in physics as bifurcations, but now, since we've become so much socialized, they call them some people call them tipping balls.
Is the magic is the buzzword.
Yeah.
So if you have a parameter like whatever alpha or something or b, I guess was there, this was some parameter mu like the intensity of solar. You have such an S-shaped curve, so this could be average temperature of the Earth, or it could be the intensity of one of those solar things. This is one bifurcation point this way, and that's the other way, and this is an unstable branch. So what happens is that if you increase this parameter, you get to here, and then you have to jump over there. But then when you keep increasing it like that, but then if you decrease, you fall off here, and so you have what's called a hysteresis. And so that was my question.
Yeah, of course.
But no, I'm just saying I don't know whether everybody here. So I'm sorry if I misplaced the alpha omega. Obviously,
No, it's correct. Absolutely. But except that we don't really know what
Yeah,
is the upper and the lower branch, of course.
So there would be just a tentative explanation that you say you don't know.
We don't really. Here's a follow-up paper of 99, post work with Steve Starr, where you then quite clearly see the superactive branch.
Okay.
But how do they, both are actually changing rotation?
Well,
that's a mechanical thing. I mean, changing rotation of a star should be quite difficult, I think.
You mean how come the star is changing this one? First, no. The star is actually breaking. So stars are born with a rotation period which is easily a day only. And then it's braked when they are not even in sequence star. And then they become up to a 30 times slower or even 100 times slower.
How do they explode the
Because of the wind. So all these stars have a wind, which is fairly small currently, but it used to be much bigger in the past. And they have magnetic lines along which they transport the stuff away. So both the solar wind, but also the interaction of the magnetic field of the star with the surrounding disk in the early ages of the star's evolution,
A primeval disk.
lead to a breaking of the central star. Yeah. And in fact, there's a angular velocity actually decays with time to the -1/2 power. This is called empirically. This is called the Schumannish law. Yeah. So therefore, it's clear that all stars are probably evolving along such lines, and they have first instability, then another one, then they work along this line and go up. So if anybody else wants to follow Peter's talk in Miso, then you're encouraged to join him and show him perhaps a way.
I can keep it later here.
What? Yes. Yeah. Good. So he has a talk in ecology. It's fun.
Okay, so obviously there's still a way to go.
Yes.
But at least these are very interesting questions. A heck of a lot more interesting to me, at least, than trying to play with error bars and establishing correlations.
Yes, I think in order to understand this one, I think the really only way forward is to have a better theoretical understanding of how the dynamos really work, rather than trying to fit it to just the sun, which sometimes works. If the sun works, then of course nothing else works. So yeah, now that so one of the things that Schlein is always saying is he doesn't think at all that the sun has any influence on the climate. He makes a very categorical statement about that.
I shouldn't,
As you might,
I shouldn't contradict him, because clearly he was my student, and now he's a really important person. But I believe that clearly it has an effect, but the fact that naysayers or deniers have been trying to use these things in order to, attack the validity of anthropogenic influences does no service to solar physics. And it sort of gives the field a bad reputation. I think it's really, it's a shame. I think it really does contribute.
Another thing that is that we haven't mentioned at all during this meeting is the influence by cosmic ray modulation, of course. And I think that's left here, but there is, as you know already, a school of people who really think that the only way to have any influence on the climate is not at all by irradiance variability, which is only 10 to the minus 3 at the most. Rather small, isn't it?
Mm-hmm.
And so only so either you do it by ultraviolet or you do it by cosmic ray irradiation, which has an influence on the lower particle.
Well, the ultraviolet, I mean, there's no question that affects the stratosphere.
Yes, yes.
Okay, I mean, the photochemistry of ozone is fairly well understood. Okay, and clearly there's a major effect on, but of course the stratosphere is only 2/10 of the mass of the atmosphere, and it's fairly well separated from the surface, and that was a matter of some argument. More recently, it used to be thought that it really had no effect on the troposphere, but now people realize that it has some effect on the troposphere. So again, I'm convinced that there's something there. The thing about the cosmic rays cloud, cloud condensation nuclei, this is much more iffy. And again, there are some people in Scandinavia who have particularly gotten out on the limb on that, in both Denmark and Finland. They are not really very much appreciated by the large fraction of the community, but I'm not that, I don't think that science is really democratic. I don't think that you vote on some Greek philosopher, Xagras or somebody said, are you going to vote in the agora that horses are asses and asses are horses? There is some such thing as objective scientific truth.
Yeah, there are these things called Forbush events, which are very strong coronal mass ejections, which are associated with immediate changes in the precipitation, I believe, or at least the cloud cover.
Well, I'm not.
Yeah, there is a student actually. I am part of the committee who is doing his PhD thesis on this. So if you want, I can. If you're interested in this, is a person that can be.
Okay. So he's working on that. What has he found?
Mike Lockwood in the University of This is ghil+brandenburg is his name. His advisor is preparing this sort of physics. So we're studying this problem both for terms of the climate impact, but the original reason is the risk for the problem spacecrafts and communication systems. Apparently there are some serious problems in that direction, but it is quite wide. What is impressive is when you see the plot in the logarithmic scales. Even in the logarithmic scales, the peaks of these events are orders of magnitude higher than the average. It's like unbelievably high. So, I don't know, there are some models, some reasons, macrophysical reasons why this should be important. In fact, in sense of process, I don't know, I'm honestly a little dubious about the extent, how strong it is with respect to the average signal. This is always my concern, and I know how easy it is. The problem is that we start to do experiments as well. And we do not know much about condensation of rain. We are not able, we are not good at describing it with models. So it's very uncertain process in itself. So even harder is to describe its variations due to the forcing element, I think. So that's my take on that.
We also have a picture that usually the way to attribute the forcing is to basically do a linear coupling. You say, and then we have the forcing, and then we add this, and then we add this, and have a linear decomposition of the forcing. And of course, that doesn't have to be the case, that the solar forcing couple linearly to the temperature. So
no,
I
but
wonder
that's precisely what these phenomena are trying to do, to be really catalysts of processes, not direct forcing. That's essentially what.
But the picture is usually seen as, oh, we have a signal here, and then we have a amplification factor. But that combined factor is seen as one component, and then you have the other component, and those are added together to get the overall picture.
About linear superposition of effects, and that some effect might be amplified but not genuinely interactive. That's true also.
I mean, the reason why I think it is worthwhile looking further at these Fawbush events is because they are very extreme events. And so unlike the average behavior, which is so weak compared with all the other extra factors, with the Fawbush events, we have really something that nobody else can compete with. And if that has an immediate, by immediate I mean on the 6-day time scale, if the strongest Fawbush events have an effect on the cloud cover on time scales of just days after the event, then that is something that has a chance in being much more accurately measurable in the next few years. I mean, obviously we're talking about events that are very strong, that have also not been monitored that carefully in the past. But given that they are happening relatively frequently, we have a chance in looking at this even in the next 3 years or in the future, very near future. We don't have to go to past records with this, which introduces lots of trouble, but we can rather go into the future in the next few years.
I don't know, I just want one question to you. I suppose that the solar effect might be more noticeable at local scales, right? So for example, if you have these deep events, then on the global average, maybe it won't be that clear, but if you go to some, scale that
I think people have tried to do that.
Lockwood has a quite recent paper where you basically say, yes, the global temperature, there is no correlation, but the regional temperature in UK is very good correlated. So it's interesting that the person who is famous for saying there is no correlation on the global scale now claims it's a correlation on the regional scale.
In that case, there is a problem of changes in the blocking. It's not. That's the claim. I think it's the paper with the thin volumes also you're referring to, probably. I don't know what.
Yes.
Yeah, because they say that there is a link between solar activity and the setup of blocking events in the Atlantic, so large-scale atmospheric phenomena, which impact directly.
Yeah.
Okay, so this is probably, so it's not a direct influence in the sense that you have an input factor and an output factor there. It is mediated through a very complex nonlinear process.
So it's a result of an amplification process.
A local amplification process.
The ocean, yeah?
I honestly, I don't know. Yeah, this is the claim. Yes, I don't know very well the paper. But
yeah, but that's probably something like this is probably the only way that we could possibly make any sense of such a claim. Right?
But again, it's not clear at all, how. I've also seen a paper of a colleague who tries to correlate, this is also not an entirely new idea, the North Atlantic oscillation with solar activity. And,
Yeah, this is about this. I mean, it's the
no,
same.
no, but this is, this is, what's his name, the Czech guy. I'll come back to me. But, I'm not convinced. I mean, I can't see, basically cloudiness is something that is due to locally vertical motion, which is due to large-scale convergences and divergences, and how those could be affected by. It's one thing to say cloud condensation nuclei, but cloudiness will not cause blocking or zone flow. It can affect whether upward motion will result in clouds or not, but it cannot give you upward motion. At least that's what I see.
It can cause if there are certain conditions it can favor, but it's a strange, it's a parametric. Setting the parameters slightly different rather than being the forcing into the motion. Especially in the case of a convection problem where you have a totally different scale. The scale is like kilometer. It's another class. It's not easy to go back and forth in this case. And
I think these questions have been addressed by those people who defended those theories, and I can't quite reproduce their arguments, but I think I'm basically thinking that the majority of cloud events really don't have much to do with cosmic rays, but those their effects averages out to zero. There's no reason why, of course, if there's no connection, then any correlation between those must average out. Now the question is really only, what about those extra events which do have something to do with the sun? I mean, there are clearly these pictures where you can have contrails or condensation or clouds above the traces of ships. You have the ship coming by the ocean, and you see clouds all of a sudden behind that, right? And it's those type of events which clearly have a causal connection with, in that case, with ships. But if there are other events which have something to do with the sun, then of course it's only that fraction that can have anything to do with what we're looking for. So therefore, if this argument of Svensson is not really easily ruled out by just looking at some simple counter-arguments which must not have a correlation. And of course, there's other arguments. I mean, there's other complications. Cosmic ray particles come in different classes. They are highly energetic ones and weakly energetic ones. And those which cause the beryllium modulation in the ice cores, I think, are mostly the lower energetic ones. And those which cause the modulation of the condensation nuclei, those are the more energetic ones. So these are all complications which need to be taken into account before one can really say, okay, there's no connection. It looks like, to me, a fairly, it looks like a workable mechanism. And if you have such a mechanism, one ought to look further into that, of course, and try to study that in further detail, which we can, I think, by looking at these forward events.
Well, I certainly think that the sun is an interesting problem, and there should be enough motivation looking at it.
So it's lucky that we didn't have a volcano yet during the present deep minimum.
No, we haven't.
What?
Now we have a second
That was a very
Icelandic
big
one.
one. What?
And now we have a second Icelandic one. We have two. Last year and this year.
Just a few days ago?
Yesterday.
A bigger one, so I will be coming back, I guess.
So then there must be really, what causes a correlation between solar activity and volcanoes?
That's an even tougher one.
But Colombia.
Yeah, that's interesting. Okay. If we call it today then? So, thanks.